Hello, so welcome to this final video for interval estimation. So basically, interval estimation is about determining the how much confidence that we have about a particular value that we get from the sample. Remember, these chapters have been leading us what we call inference. So inference is basically about trying to estimate. You're trying to estimate the population characteristics using a sample. This is basically most of what you do in statistics, because it's usually expensive to do what you call a survey. Survey is what happens when you actually try, or rather, it's usually difficult to do what you call a census. So a census is when you take every member of the population. So a lot of the time, this is not actually practical. So what you really want to do is to get a sample and then estimate. You get a sample and then you estimate the population characteristics, and the value that you do get, we say is referred to as a point estimate. So the value you obtain, and the value you obtain is a point estimate. So for instance, you could get a mean. We've been looking at means and proportions, proportions. So you could get a mean or a proportion, and you want to see determine how representative is this mean going to be of the actual proportion. And in chapter 7, we looked at what we call a sampling distribution, which is basically the shape of if you look at that point estimator and you're trying to see what is this probability function, it's probability density function, and this allows you to get some idea of how much confidence you should have about a particular value. So I think it's best to explain this with an example. So let's look at one example here. So you have this store that we call a Lloyd's department store, where they do this study, a random sample of 100 customers. So you know that n, lowercase n, is, you know that n is equal to n is equal to 100. So this is the sample size, and then you know that the so according to this information, blah blah blah, we have a known sigma of 20. So we have a known population sigma. Sigma is going to be equal to 20. Then what other information do we have? So according to this information over here, then we have a mean. So this is the sample mean. So we have we're gonna need one of these. So we have a sigma x, an x bar of 82. So this is the sample, the population, the sampling distribution mean. So we could be interested in, usually you want to know, for instance, where 95% of the values lie with respect to the sampling distribution mean, which is also the population mean. So we want to see where 95% of the values that we get for mean, if you calculated a mean, what 95% of the possible values lie. And if you use the empirical rule, the empirical rule comes directly from the shape of a normal distribution curve, because if we do assume that this is a normal distribution curve, then the empirical rule can apply. So remember, if you use the empirical rule, then we know that at least 95% of these values will be within 1.96 of the mean of the sampling distribution mean, which is also the population mean. So if you want to know where 95% of these values lie, then we know they are within 1.9% standard deviations. They are within 1.9% standard deviations, 1.96 standard deviations of the mean. So all you have to do is to calculate the sampling standard deviation in that case, because it means that basically the error is going to be equal to plus or minus. So the error is going to be plus or minus 1.96 of the sample standard deviation. So at this point, we actually have the error already simply by applying the empirical rule, and so I could basically stop the lecture here, but let's go ahead and see what that actually means. So I need to have a symbol and a symbol, yeah. So I'm basically saying that this is going to be the error for 95% for a 95% confidence interval. For 95% confidence interval, this is basically the error. So anyway, so what does this really mean? So remember that the equation for this sampling standard deviation is going to be I'm going to need one of those. Then I'm going to need to insert a sigma. So the sigma x is going to be equal to so we say this is going to be equal to 1 is going to be equal to just a minute, plus or minus 1.96 sorry, talk about sigma x. So sigma x is going to be equal to we're going to need an equation. So usually, so in the general case, we say you need to have a finite population correction factor, which is basically minus, and then you have where that uppercase n is basically the population size. So, but we say if okay, let me just finish this out first. So let's say you're gonna have to multiply that with the other equation. So the other equation is you want to get one of these, and then you have what's the uppercase. So you have the population standard deviation in this case. So the population standard deviation is given by a sigma, and this is going to be over root. Just a minute. It's going to be over root n. So this is the general case, but where I would say if n is small, lowercase n is small relative to n, if it's less than or equal to 5% or 0.05, then you could ignore the population correction factor, because this term is actually going to tend to 1. So we're going to assume that is the case. So that means our sample standard deviation is simply going to be sigma over root n. Sigma in our case is already given to be in this example. Sigma is 20, yeah. So our sigma is already given to be 20, and then root and n, and we know n is 100, so root n is 10. So sigma is actually 2. So if we substitute in this equation, then we know that 95% of our values are within 2 plus or minus 2 times 1.96. So we have an error over, so basically our error is going to be plus or minus 1.96 by 2. I just need to do this real quick. 1.96 by 2. So we know that our error is going to be 3.92 plus or minus 3.92. So this is how you estimate the error. It will be plus or minus 3.92. In general, you can talk about what you call the alpha value. You can talk about what you call the alpha value. I just need a okay, here it is. Okay, so here we are. So we talk about the alpha value. So the alpha value is basically 1 minus the why did you do that? So we have the alpha. So the alpha value, and the alpha is basically 1 minus the confidence interval. So this is actually equal to 1 minus the confidence interval. So the alpha value is basically we're trying to see the value which is 1 minus the confidence interval. So if you have a confidence interval, say our confidence interval is 95%, the confidence interval is equal to 95%, 0.95, then the alpha value is going to be so the alpha value is actually 0.05. Yeah, is actually 0.05. So knowing the alpha, if you want to compute the error, error is going to be equal to, so now we're going to have a general formulation for the error value. So the error is actually going to be equal to it's going to be equal to plus or minus z. So I just need a new equation here. It's going to be equal to plus or minus z at alpha. Just a minute. Z at alpha over 2, and this is going to be multiplied by sigma, and this is multiplied by sigma, so this is multiplied by sigma over, and then we have sigma over root n. So this is basically the general form this is basically the general form for the equation for the error. So if you just go back to what we had before, so this is how we had the error. So you're saying this is going to be basically plus or minus alpha z alpha times sigma over root n. So sigma over root n is over here in the previous example, and then we're saying this value here we can actually obtain it by getting z alpha over 2. So if I just take you back to the general expression, so we have this expression here. So anyway, let's see. So we're saying this is z alpha over 2. So basically, this what this really means is that you're getting the area, you're getting the z value or the area for alpha over 2. So or rather, you're getting the value which has got an area of alpha over 2, a cumulative area of alpha over 2. So we say for it, so that basically means you're getting the if you go back to the cumulative probability distribution table, so we can see 0.025 is actually here at 1.9. It is actually here at 1.9. So you have a value of minus 1.9 or 0.025. Let's just see the other side. So again, so we have a value here of 0.9750. So So the value is actually 1.9. Yeah, the value is actually 1.9. Where you actually get this value of 0.025. So that is the z alpha over 2. So it's not exact, but we know the value is actually 1.9. And 1.9, if I do clear, 1.9 times 3, rather 0.2, it gives us 3.8. So this is not exactly the value that we had before, but it's pretty close. So the difference is a 0.2. So that is just a result of how exactly we are calculating this. So before we're doing the exact computation, but we said the tables have got a limit of accuracy of 1 decimal. The limit of accuracy is 1 decimal place on the z in the z column. So that's the why we have the small difference of 0.02. So yeah, so this is basically how you do it. And this gives you something which is very close to the 3.92 that we had before. So you could actually flip this if you wanted to get the, if you say instead now we want to get the value of n that gives you a particular error, that gives you a particular error bounds, then you can simply make n the subject of the equation. So from this, it basically means that root n, let me just get a new equation here. It basically means that that root n root n is equal to, so we know this to be, this is essentially, so let me just insert a new symbol. So that is essentially plus or minus z. Let me just insert new, so that's plus or minus z alpha over 2. Z alpha over 2. So this expression over here is alpha over 2. This value over here is alpha over 2. And then this is going to be times. So you're multiplying all of this by z alpha over 2 times, so you have this fraction. So now it's going to be sigma. It's going to be sigma over e, right? But remember, what we actually want is n. So if what we want is actually n, then this is going to be equal to the square. It's going to be equal to the square of everything this side, right? Okay. It's actually going to be equal to the square of everything I should have had one of those, then I have everything squared. So this is basically going to be the expression that gives you the number, the size of the sample that you need to get in order to obtain a particular E. Yeah. So this concludes basically how you do it. If you have this concludes basically how you get the bounds if you had a known a population standard deviation. Remember, this needs you to have a sigma. So if you have a known population standard deviation, then you can compute the error bounds and also the number, the population, rather the sample size that you need to get a particular error bound using the expressions that that we've been going through. So in the next lecture, we're going to be seeing how you do this if you do not if you actually do not know the population standard deviation.